This video tutorial is about light, and we're going to go through just the basic things you need to know about light at the beginning of this unit. So the first thing that we're going to talk about is what light actually is, and then we're going to talk about what its wave properties are, and then we're going to talk about the electromagnetic spectrum. So let's start out with what is light. Well, light is a form of energy. It's also called electromagnetic radiation. And light actually travels through the air in waves, a lot like sound, only sound travels a lot slower than light. Some forms of light are visible, like, the kind of light that comes from the sun or a light bulb. And some kinds of light are invisible, like radio waves, X-rays, ultraviolet rays, infrared radiation. These are invisible forms of light. Light's kind of a funny thing because even though it is a form of energy and it moves like a wave, or it acts like a wave, like ripples in water, right? It also sometimes acts like a particle, meaning that it can collide with electrons and it can kind of knock them around as if it were made of something that had mass and volume, even though light doesn't have mass and volume. So to say that it acts like a particle is something that we're going to talk about later. Today we're going to focus on its wave properties. So let's do that. Let's talk about the wave properties of light. All waves, including light waves, have a few properties we need to define. So the first property of a wave is called wavelength. And wavelength is measured in meters, and it is exactly what it says it is. It's the length of the wave. Wavelength has a symbol. The symbol for wavelength is this symbol right here. That's called a Greek lambda. And so whenever you see a Greek lambda, so this symbol right here, we are talking about wavelength. So to measure the length of a wave, well, first of all, you need to be able to detect that wave. And since you can't actually see a light wave, you would need some sort of instrument that could detect that wave, and then you could get a picture of the wave and measure its length. But so assuming that I give you a picture of the wave like I did here, to measure the length of the wave, there are a number of ways that you can do this. So you can go from crest to crest. So the top of a wave is called its crest. And if you measure from one crest to the next crest, you can get the length of that wave. Or you can measure trough to trough. So the bottom of a wave is called a trough. And if you measure from one trough to the next trough, you also get wavelength. Or you can go node to node. So node is where it crosses the line. And then you want to go not to the next half node, but to the next full node. So from here to here is also wavelength. And all three of those should be exactly the same as long as that wave type isn't changing. So as far as wavelength is concerned, we have a range here. Like radio waves, 1 × 10 to the second meters is the length of a typical radio wave. And that's a type of light. And then so we have a very long wave, right? As opposed to something like gamma radiation. So gamma radiation, which we talked about in the last unit, gamma radiation is a high energy light with a wavelength of 1 × 10 to the negative 14 meters. So it's got really, really, really short waves, right? They're very close to each other and have a lot of energy. And so those are about the ranges of wavelengths you'd find for light. And then, of course, there's all the ranges in between, or all the types of light in between, which we'll talk about here in a minute. The second property of light waves that I would like you to know is frequency. And frequency is measured in something called hertz. Sure, you've heard of the car rental place. That's not the same thing. Okay, hertz is equal to, so 1 hertz is equal to 1 wave per second. So hertz are waves per second. And you abbreviate hertz, HZ. So it's really measured in waves per second, but instead of writing waves per second, we write hertz. Great. So frequency is a measurement of the number of waves that happen every second. And so if we were to look at this picture that I have here, assuming, you can ignore these headings right here and here. Let's just look at the wave. So if we assume this is 0 seconds, and this is like, say, 2 seconds. So here, 0 seconds, and this is 2 seconds. Well, you can see that one of these waves is happening more frequently than the other. The first wave, we'll say, is wave A, and this is wave B. Wave A is happening, let's see, you've got a total of 1, 2, 3, 4, 5, 6 waves happening in 2 seconds, which gives that a frequency of 3 hertz. Whereas wave B is happening, or has 1, 2, 3 waves happening in the same amount of time, 2 seconds, which gives it a frequency of half, or 1.5 hertz, which is half of the frequency of the other, right? So this is clearly a higher frequency wave, right? It's more frequent. It has a higher frequency. All right, and this is, of course, a lower frequency comparatively. Okay, so frequency also has a Greek letter designation, just like wavelength was lambda. Frequency's symbol is this. Its symbol is this thing right here. And that, I believe, is a Greek letter nu. So it looks kind of like a V, but it's not. And the frequency of waves, so radio waves, which are the lowest frequency wave, or they have a frequency of about 3 times 10 to the 4th hertz. So that's radio waves, all the way up to gamma radiation, which is 3 times 10 to the 22nd hertz. So clearly a lot more waves per second for our gamma radiation versus something as low as radio waves, right? So if we were to look at, what kind of wave we're talking about here, again, very long waves versus really short kind of, waves with very short wavelengths. Okay, the last property of light that you will be expected to know, or of light waves, is something called speed. Now, don't get speed mixed up with frequency. It's very, very simple to mix the two up. So the speed of light is measured in meters per second. So as opposed to waves per second, this is meters per second. So this is actually a speed. Waves per second is not a speed. That's a frequency. This is speed. So this is how fast, how many meters light travels every second. It's got also a designation. This time it's not a Greek symbol. This time it is just a C. A capital C is the speed of light. And the speed of light actually has a value, a known value that doesn't change. And you need to memorize this number. So the speed of light is always 3.00 times 10 to the 8th meters per second. So it doesn't matter what kind of light we're talking about. Radio waves, X-rays, visible light, gamma rays, all light travels at that speed, and you need to know that speed. You need to memorize that number. So let's quickly have a little conversation about the relationship between wavelength and frequency and the energy of a wave. So we just talked about what wavelength and frequency are, and they are related to each other. So if you look at something like this first wave right here, which will designate wave A, and then this will be wave B. Wave A, clearly, if these two things took place in the same amount of time, so this is 0 seconds, and say this is 2 seconds, and then this is 0 seconds, and this is also 2 seconds. Okay, you can see that wave A was more frequent. There was a lot more waves in that 2 second span of time than the second wave. So more frequent waves have shorter wavelengths. So if you look at the wavelength of wave A versus the wavelength of wave B, so if you measure from here to here versus from here to here, you can see that wave A has a much shorter wavelength and a higher frequency. So shorter wavelengths have higher frequencies, and lower wavelength waves have lower frequencies. They happen less often. You need to know this relationship because this relationship has an equation. The equation is C equals lambda nu. So what that means is the speed of light, C is the speed of light, is equal to the wavelength of that light times its frequency. And that means that if you have a higher wavelength, you're going to have a lower frequency. You're always going to know the speed of light, right? The speed of light is always the same number. It's 3.00 times 10 to the 8th meters per second. And so your wavelength and your frequency multiplied by each other should always equal 3 times 10 to the 8th meters per second. And so what that tells me is that if I have a high frequency, I have to have a lower wavelength to make sure that when I multiply them together, they always equal 3 times 10 to the 8th meters per second. And you will be making calculations with this equation quite a bit, so you're going to want to make sure that you write that down. At some point, you're going to be making calculations for energy of waves as well. We're going to leave that for later in this chapter. But right now, we do need to just have a little conversation about the energy of waves, just relatively. So that being said, you can look at these two waves, and you can imagine that these are water waves when you're thinking about the energy of these waves. So let's say you're standing in the pathway of these, and they're water, right? So there's you, standing there. And this is a bunch of waves coming at you. Which one would be more energetic? I would think that the higher frequency waves would have more energy because there's more coming at you more frequently, and that would kind of, it would be hard to stand in that, right? So that being said, the higher the frequency, right? So the higher the frequency, that means that you're going to have a higher energy wave. And the lower the frequency equals a lower energy wave. And another way you can say that is, instead of talking frequency, we can talk wavelength, right? So the longer, or rather the shorter the wavelength, so low wavelength, short wavelength, is going to be high energy, right? Because that's more frequent waves, whereas longer wavelengths are going to be lower energy waves. And you need to understand that relationship. It's very important that you do. When we talked about gamma radiation is the shortest wavelength light there is, which means it's the most frequent and the most energetic. All right, so let's talk about the last little topic that we need to talk about, which is the electromagnetic spectrum. So here's the electromagnetic spectrum. Now remember, electromagnetic spectrum refers to light, right? So electromagnetic radiation or electromagnetic waves, that's just a fancy word for light. And so we're really talking about what spectrum of waves, what range of waves would we consider light waves. There are all kinds of waves. You've got sound waves, and you've got mechanical waves like waves in water. Well, when we're talking about waves that travel through the air, anything within the range of from, say, I don't know, this was about 10 to the second meters, all the way up to 10 times, to the 14th meters. Those lengths would be considered in the electromagnetic spectrum. And then, of course, you've got your range of frequencies here along the top. And so here's all the different kinds of waves. So I will give you a copy of this in class, just so you know, but you need to understand that the shortest wavelength of waves, or rather the longest wavelength of waves, the shortest frequency, is radio waves. So they have the least energy, right? So if we're going to go energy is going to increase in this direction. And you've got wavelength, right? So wavelength is actually going to increase in this direction. And then you also have frequency, and your frequency is going to increase in this direction. So frequency and energy increase in the same direction, and wavelength is the opposite. And you've got all kinds of different kinds of light here. You've got radio waves, TV waves, microwaves, infrared. There's this tiny, tiny little sliver in the middle that represents your visible spectrum, and you need to know your visible spectrum. And hopefully you remember this from school, but you've got red, orange, yellow, green, blue, indigo, and violet. So Roy G. Biv is your range of light or visible light, and then beyond that you have ultraviolet X-rays, gamma rays, and then the worst cosmic rays, which I don't think we have to worry too much about here on planet Earth. So that's your electromagnetic spectrum, and you need to be able to calculate a wavelength or a frequency from each other, and then figure out what part of the spectrum those lie in. And don't forget, I did give you an equation for calculating frequency frequency or wavelength, and you should be able to do that easily, calculate one or the other, and then just look it up on this particular spectrum. So that brings us to the end of our presentation on the basics of light.